Okay. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Today's lecture will be a little bit dense in terms of material, uh, but no abstract stuff. So it's a lot of computations. So that's why you need actually to do all of these computations yourself. Today I'll be walking you through some of many properties you're going to be seeing of rigid body dynamics and all of the all of the variables that appear in it. You should know, okay, from the basis of what we discussed, what the meaning of all of these matrices and vectors are. So this is very important. But in the end, what we're going to be doing is matrix multiplication. So that's it. So if you know how to work with matrices, everything today should be familiar. You only need to work out these, properties yourself. That's why today, inshallah, to rely a lot on homework number 3 and assignment number 3. I'll try as soon as possible, inshallah, to post them. If not today, then tomorrow, inshallah. Then I strongly suggest, you start doing them. And to enforce you, okay, / to motivate you, we'll have a quiz next week, okay, for that. And we'll discuss at the end, inshallah, okay? Yes.
The algebra of special orthogonal three, which is the tangent space of the identity.
The Lie algebra of the capital SO3, of the Lie group SO3, is the tangent space at the identity, yes. If you say it's the Lie algebra of the Lie group. So the Lie algebra itself is called small SO3, and the capital SO3 is the group.
Special body angular velocity be the same in some special cases.
I don't. Can they be the same in some special cases? I don't think so. We can look at the math. We're going to do a recap now. So when you come to that equation, just point me out, okay? Stop me here, okay? So let's start with the recap. We said when we're doing kinematic modeling, the first thing you're going to be doing in your robotic system of choice is that place frames everywhere, okay? So any body that's moving, okay, even if you have somebody that actually, that, for example, even on the same body, you might actually have multiple frames. You just add all of the frames that you're interested in, and you describe the relative pose between any of these two frames by a homogeneous transformation matrix. That's an element of SE3. And in the end, inside, the only information there is just a rotation matrix in SO3 and the translation vector in R3. Then we started looking at kinematics, which means that we need to look at the rate of change of these variables. So what you should know from simple physics or from simple mechanics course is that the point translation dynamics is simply that you have the configuration and you have the rate of change of the configuration, you have the velocity, and rate of change of position is equal to velocity. That's the simple point dynamics that you should be familiar with. When we went to rotations, we said, okay, we have the configuration is a rotation matrix. The rate of change of configuration is a vector at the tangent space to that configuration. And angular velocity can be described, okay, by this Q-symmetric matrix. And this Q-symmetric matrix lives in the tangent space at the identity, which was what we called the Lie algebra of the Lie group. The term algebra itself actually is an extra structure on a vector space. I'm not going to go into that for time reasons, but look that up on your own, okay? So to look at what do we mean actually by an algebra? You'll find that it's a vector space plus extra structure. And the kinematic relation between the rate of change of this variable and the angular velocity was given by one of these two equations. They are exactly the same, okay? They are just whether we do a right translation or a left translation, if you remember from the abstract notion from last time. And the right translation and the left translation to the algebra is nothing else than right multiplication by the R or left multiplication by the R. This abstract picture is exactly what you have even when we go to SE3. Everything is exactly the same. We have the configuration, which is now this expanded matrix, and the rate of change of configuration is again a vector in the tangent space. The element of the algebra now, and this algebra is now small SE3, is also the tangent space at the identity, and we call the elements there twists. Okay, so and it's again in some sort of matrix form. So here this was a 4x4 matrix in 3. When we were talking about SE3, 4x4, 4x4, and another 4x4 matrix, and they are related by one of these two equations. Okay. Then we said that when we looked at the structure of a skew-symmetric matrix, we found that essentially it's actually just 3 numbers. And this should ring a bell because if you remember at some point when we were discussing bases, Okay, and we said that SO3 actually has a vector space structure, and we introduced 3 bases, and we said that the dimension of SO3 was in the end actually 3. Even though we have 9 numbers here, but I have in the end 3 bases. I can always represent this matrix as the sum as 3 elementary skew-symmetric matrix. You can go back and you can check them, which means that the dimension of SO3 was actually 3, and this means that actually it's isomorphic to R3. This isomorphism in the end is simply, you look at this matrix, okay, and you pick up this element and you call it element number 1. You look at this element, you call it element number 2. You look at this element, you call it element number 3. Okay, and if I tell you what's the inverse of that map, you say me, okay, yeah, I'll give you 3 numbers, put them in this order, and that's it. So this is actually, this is actually what the map is. If I ask you to write a MATLAB code describing this, is it easy or not? It's trivial, right? How you can write. This is a map. So now you see, you're not just you're not just, even though you thought of maps or functions, that's something, that takes something and puts it into like an equation or something, but these are also maps, and you've been thinking about them, okay, in many scenarios, and this is a typical scenario where you go from R3 to SO3, and actually this is an isomorphism. So this, talking about R3 or talking about SO3 is the same thing because of this structure. Then when we looked at SE3, we found that any element of SE3 will have this special structure. All of the bottom row will all be zeros, and on the top left corner you're gonna find a skew-symmetric matrix, and on the top, okay, on the right corner you're gonna find a 3x1 vector. And in the end, we can actually have an isomorphism to 6 numbers, which is what we're gonna be calling the angular velocity and the linear velocity. So the twist is nothing else than, okay, the combination of angular velocity and linear velocity in one object, in one simple object. Any questions so far? Okay. Now let's look a little bit of the properties of twists. So from now on, okay, all of the abstract, annoying, okay, information will go to a minimum for some time, and then we're gonna come back later after the midterm, inshallah. But at least for now, everything will be just playing around with numbers, okay? But you have to appreciate that, okay, when you look at this 6x1 vector, what is the meaning of it? Today, we're going to be hopefully appreciating this more and more. One of the very important things about working with twists and angular velocities, again in skew-symmetric form, is that they have a vector space structure, which means that if I have, for example, a scenario where I'm interested in the angular velocity of the end effector with respect to the base, and then at some point I actually have the base with respect to the end effector. How do I read these to each other? By minus sign. Okay, the same holds for angular velocities, and it also holds for twists. Whether in the tilde form, okay, or in the vector form, we have the same equation exactly. Okay, so nothing else changes. Okay, and if I have, for example, the end effector with respect to the camera, and the camera with respect to the inertial frame, then what is the end effector with respect to the inertial frame? You can just simply add all of these together. So in the end, if I have I with respect to k, it's equivalent to I with respect to m plus m with respect to k. Whether in tilde form or in vector form, this also holds for SE3 and, okay, the R6 vectors. So in the end, something that if you remember the first time you were introduced to, hopefully, mechanics, when you were introduced just to linear velocities, everything was easy. When you went to translation and rotation, things become very nasty. But you see in this language, it's actually very easy. We still maintain the same simplicity as my velocity with respect to the laptop is the laptop's velocity with respect to the car, and so on and so forth. Okay, so we have this simple addition here, and it makes life easier. And you're going to see that we're going to be using this very simple property again and again and again, because there is no end. You can sum as many as you wish. Just as a teaser, imagine that you have a robot arm, okay? And for example, you want the end effector with respect to the base of the robot. Then you would say that the end effector, the base of the robot with respect to the first link, plus the first link, plus with respect to the second link, plus the second, plus, and so on and so forth, until you reach the nth link with respect to the end effector. And you would still have something like this. We're going to come to that later, inshallah. Now, a question that you should ask yourself, which is now something to note very importantly here is that all of these equations, they only hold in one frame. Okay, so you see all of this green star is very important. They have to have the same frame. Okay, That's very important. And now one question might arise. If I have some angular velocity expressed in one frame, how do I relate it to an angular velocity in another frame? And similarly, if I have a twist in one frame, how do I relate this to a twist in another frame? Okay, because we need these transformations again and again as we move on. So two important objects were introduced so far, okay, which are very natural. If I'm talking about the angular velocity of the frame B with respect to frame S, then it's natural that I express it either in S or in B. We call that the angular velocity expressed in S the spatial angular velocity, and the angular velocity expressed in B the body angular velocity. Both of them were related by this equation. Make sense? Okay, so in the end, whether I left multiply the body angular velocity or right multiply the spatial angular velocity, in the end I should get R dot. Which in the end, if you look at this equation actually, then these two should be equal to each other. Then simplify, multiply by the left or by the right one of the two R's, the inverse of one of the two R's, and the inverse here is just the transpose. We get in the end this equation. Make sense? So this is exactly how you transform from one R, from one angular velocity to the other. You just multiply from the right and from the left by a R matrix. Of course, the indices you have to be very careful, and there is also a very nice trick, okay, that you can, again, so that you can never make mistakes there. You see here, this is expressed in the B frame, right? So this one has to take it from B to S. You all agree? Then on the other side, it has to be from S to B. That's it. Okay. So if this is an angular velocity, it's expressed in B. I multiply here from something from B to S, and I need to multiply from the other side by the inverse from S to B. So you always have like something like SB, B, BS. You always have this, you know, this like chain rule. And in the end, this is just simply what it is. As simple as this. If you work out this expression, okay, so this is in the tilde form. This is as a skew-symmetric matrix. Now, a natural question is, how are these two vectors related to each other? If you work that out, you'll reach, okay, this expression, okay, that we have that the body angular velocity, if I want to transform it to the spatial angular velocity, I need to multiply it by a special matrix, okay, that usually comes for every Lie group. Every Lie group would have some sort of matrix that looks like this. And this is usually called the adjoint map of the Lie group. Okay? In this case, we're talking about the Lie group SO3. So this is the adjoint of SO3. And usually it's a function of R, or the function of the configuration. So for example, if I have the Lie group, if I have the adjoint representation or adjoint map of SO3, it will be a function of R. When we talk about the adjoint map of SE3, it will be a function of H, and so on and so forth. In this special case where we have, okay, SO3, the adjoint function is simply R. Okay? So transforming from B to S is nothing else than multiplying it from RB, okay, to S. That's it. You can actually show this. Okay? I'll put it for you in the reading material. Okay? So it involves a little bit of, you know, some calculations. It's just half a page, but in the end, you can show it for yourself. Okay. And from now on, you can always think of it as actually some sort of property that if the tilde form, okay, is transformed by pre-multiplying and post-multiplying by an R, the vector form will multiply it by an R. That's it. Okay. Any questions so far? Make sense? Okay. We're gonna have a lot of this lecture. We're gonna have a lot of, I'll tell you, it will look like that, but I will not show it to you. And this is what you're going to be doing either at home, okay, at your own pace. So you really have to do these calculations yourself, okay, so that you're really convinced that this is truly the case. Yes.
If I want the reverse, which is omega b relative to S expressed in B,
Yeah.
equal to the adjoint map or SB.
SB. And RSB or RBS or any R here is always R. The adjoint as a function of R is always R. You see, this is what this equation means. Okay, which is exactly the intuition that you should have, that if I have a vector expressed in B and I want to transform it to S, I just multiply by the rotation matrix from B to S. And if this is a vector expressed in S and I want to transform it to B, I just multiply it by R S to B, and so on and so forth. You'll always have this intuition. Okay. The reason why we talk about the adjoint map is that imagine now if we go from SO3 to SA3, how different will it be? It will be exactly the same. This one is like it. It is like it a little bit. Yes, it is like it. Okay.
And also this one add R times omega is something like also B times like changing the basis also.
No, changing basis. It is exactly changing the basis. Yes, that's right. That is right. But this is not a similarity transformation. Okay, because you remember a similarity transformation will be introduced for bilinear forms, but a transformation for vectors, okay, was simply multiplying by exactly what you said, like a p, like a change of basis. But this is not a similarity transformation. This is just an identity. If the vector is transformed by some matrix R, then the tilde form of that vector will be transformed by R.
We can do it like this because it is left in vector space now.
Yes, exactly. So it is a vector. This is a vector and this is a vector. They're just two representations of the vector. This is very important. If you look at this, you see these are two vectors. This is a vector in R3 and this is a vector in SO3. Both have vector space structure. Good. Now, if you go to SE3, you'll find that I have the twist expressed in the S frame called spatial twist. I have the twist expressed in the body frame. We call it the body twist. The spatial frame has two components. Sorry, the spatial twist has two components, an angular velocity in the S frame, a linear velocity in the S frame. The body twist has two components, an angular velocity in the B frame and linear velocity in the B frame. How do I relate this to that? Simply, if you look at the H dot was equal to this expression plus this and this expression at the same time, which means that these two should be equal. Then if you look at this expression, we have exactly the same. Everything is exactly the same. This is expressed in B. Then I have SB, BS to go to the S frame. Make sense? Okay. Natural question is, if this is how the tilde form of the twist changes coordinates, how does the vector form changes coordinates? What do you expect the size of the map that will transform from one frame, from one twist to the other? Well, what the size of it should be? Should be what? So what's the size of it? If this is a 6 vector and this is a 6 vector, a 6 by 6 matrix, exactly. So this 6 by 6 matrix is also called the adjoint matrix. You see now it's a function of H, not a function of R. This is also what you get from the Lie group. So it's called the adjoint map of the Lie group. And how does this map look like? That's for you to do in the homework, okay, or the assignment. Yeah, that's the homework. Okay, you have some stuff in the assignment, some stuff in the homework. Okay. So, and this is how it looks like. It's a 6 by 6 matrix. If you look at the top left corner, you find an R. You look at the top right, the bottom right corner, you find another R. You look at the top right corner, you find a matrix of zeros, a 3 by 3 matrix of zeros. And in the top and the bottom left, you have the tilde form of psi multiplied by R. So R is a 3 by 3. Tilde form of psi is a skew symmetric 3 by 3 matrix. So 3 by 3 multiplied by 3 by 3, you get a 3 by 3 matrix. So 3 by 3, 3 by 3, 3 by 3, 3 by 3, you put them next together, you get a 6 by 6 matrix. Why does that joint look like this? Very easy. Take this equation, expand it out, start to play around with some algebra, okay? And just in the end, look at how, compare the right-hand side and the left-hand side. You'll find that actually to write this expression, naturally the adjoint will be like this. That's exactly what you're going to be doing in the home. Okay? Make sense? So this is called the adjoint map, and it will map you from one twist to the other. Any questions so far? Okay. Now let's look at some of the properties of this adjoint map. So this adjoint map will take you from R6 to R6, and this is again how it looks like. Some of the very nice properties of it, it's not just any 6 by 6 matrix. It comes actually from the Lie group. And remember what we said about the Lie group. The Lie group is a group and a manifold. So you expect the more structure we have, the nicer some of the properties will be. Okay, so we're going to have what you usually say closed form expressions, closed form solutions for some of the very nice things. One of the very nice properties we're going to have is actually, if you compose two adjoints, is exactly as taking the adjoint of the composition of the two edges in the same order. There's something very nice. If you take the inverse of this 6 by 6 matrix, is exactly the same as taking the adjoint of the inverse of the H matrix. Okay. And if you take the time derivative of this matrix, which is an expression that will be very important, you're going to see later why. So when we take the time derivative, first of all, where is time here appearing? What is here actually a function of time? The h itself, right? You remember we said when we have the manifold and the h itself changes at every point. For example, you have a drone, and the drone is flying and is doing like this. So as a function of time, its pose is changing. Or you have a robot and the end effector is changing as a function of time, or each body is changing as a function of time. So in the end, the h itself is here the function of time. So add the adjoint as a function of h. If you take the time derivative of that, you'll find that will be equal to the same adjoint matrix multiplied by another expression, okay, another 6 by 6 matrix. That's a map from R6 to R6. That actually is called the adjoint operator of SE3. This actually is just a type. It should be small SE3. This small adjoint is the adjoint of the algebra, while this capital adjoint is the adjoint of the group. So you see that they're actually related to this Lie group theory. Any Lie group will have an adjoint and a small, and its corresponding algebra will have a small adjoint. And this actually expressions, they appear a lot, and you can do, if you master these tools, you can do a lot of, very cool stuff with it, okay? Way beyond just, rigid body dynamics. But here, this is the map that will appear a lot. How does this adjoint look like? It's simply, first of all, this adjoint is a function of the twist. So the adjoint now is a function of twist. The capital adjoint is a function of h, but the small adjoint is a function of twist. Okay? And that makes sense, right? Because here we took the time derivative, and this was a function of h. So it's like you have a chain rule, right? You have the add of h, and you have like the add something like with an h dot, and the h dot is related to the twist. So this is actually how where the twist comes from. So what you're gonna be doing is that in the assignment, you're gonna be working out this expression. You're gonna be showing really, if I took the adjoint, which is this expression, and I just take the dot here and the dot here and so on and so forth, and I again play around with some matrices, you can actually show that the small adjoint has this structure. It's a 6 by 6 matrix, which again means it has 4 blocks. Top left corner is omega tilde, which is in skew symmetric form. Bottom right corner is omega tilde, skew symmetric. Bottom left corner V tilde. Top right corner is a matrix of zeros, 3 by 3 matrix of zeros. Now, very quick IQ question. Is this skew symmetric?
No. Because no.
Who says yes? Yes.
No.
Who says no?
We
Okay.
need this left element to be in the right element, some mirror with negative.
Exactly. So if for this to be skew symmetric, how can you check whether something is skew symmetric or not? You just take the transpose of it. So what is the transpose of this matrix? The diagonal blocks will be transposed. So this will be omega transpose, and this will be omega tilde transpose. And the off diagonal terms, they transpose, but they also change their order. They don't change signs. They change their order. This is what the transpose does. So the 0 will become here, and the V tilde will become there. Okay, but the V tilde will become transposed. Now the tilde, any tilde matrix is actually a skew symmetric one, which means that the transpose of it is actually minus. So this becomes minus omega tilde, minus omega tilde. This becomes 0, and this becomes minus V tilde. So now if you compare the two matrices, are they one minus of the other? And the answer is no, because this was actually just a V here. What is needed here for this to be skew symmetric? Instead of the zeros, you have V tilde. Exactly. If you have V tilde here, then this becomes really skew symmetric. No, V tilde. Not minus, because no, not minus, because when you transpose it, it will have the minus sign. Make sense? So if this one, you need to check that add V transpose is equal to minus add V. Okay? That's an exercise for you to try at home. Make sense so far? Okay. So that's it. That's all the math that we need. You see, as I promised, they're all just matrices, okay? And again, you could have skipped topic number 1 completely and just entered, by working with the 6 vector and working with, the 6 by 6 matrices and just, crunching number. I don't know how you would leave it to yourself. I cannot, okay? So now let's look at dynamic model. So what we're going to be doing right now is that we're going to be taking all of these tools and writing the equation of a rigid body. Okay, the equation of motion of a rigid body. We're going to be looking at, something like Newton's law. F is equal to ma, and definitely we're going to be talking about the acceleration. So you know how to do, okay, forces translate on a translating mass. So this is just the point dynamics. Torques on rotating rigid body. Okay, you can imagine now that we need to work with SO3 here. And now if you have full rigid body motion, then we actually have SE3. So here, if we have a point mass, you're introduced to that concept of velocity and force. If you have something that's rotating, you have angular velocity and what's it called? Torques. What is the name of the velocity, like variable that we called for rigid bodies? We call twists. What will be the corresponding something like a force that acts on this body will be called a wrench, exactly. Okay. So from now on, forces and velocities, torques and angular velocities, and wrenches and twists. Okay. If the twist itself was nothing else than angular velocity and linear velocity, what do you think the wrench will be? Forces and torque. That's it. Okay. So now let's look how they look like. I'm just going to remind you of what you should know from about point masses, and let's see how this translates to rigid bodies. With point mass dynamics, you say that I have a point. There is no orientation. It's just a point there, and it's moving. So there is this vector, and there is a force applied on. There is a force applied on the point B. And now we're going to be differentiating between two things, between a force abstractly and how you represent the force, in which frame you're going to be representing the force. In this scenario, we only have one frame, which is the S frame, the inertial frame. Later on, we're going to have more frames. Okay, so you can imagine how things will be more complicated. But for now, the F, when we write F source down and B up, and it's a R3, we actually mean the abstract force from source SRC acting on the point mass B. If we put on next to it an S, it means that we're representing this force in the S frame, okay, so that we can get numbers. So this is an abstract force, and this is the numbers. How is kinetic energy defined? Half mv squared, right? But if you have something that's moving in 3D, then you just simply have half m v transpose v. This is just the v. I'm just giving it all of these indices so that you can be very aware that this is the velocity of the point mass with respect to the spatial frame, with respect to the inertial frame, the one that's fixed, expressed in that inertial frame. So this is BSS. Okay. Of course, when you're working, standard mechanics, you don't put all of these indices. You just say half mv transpose v. Okay? And this is the kinetic energy. How is momentum defined? How do you define momentum? mv, right? Where did this come from? Exactly. Okay, not a lot of people know that, so that's good. If you take the kinetic energy and you take the gradient of it with respect to the v, this is actually the definition of momentum. So if I look here that I have half m v transpose v, what is the gradient of this expression with respect to the v? It's just mv, and thus we define this to be actually the linear momentum. Okay? This is the relation why this is linear momentum. I don't know how you called it, like P or like H or L, doesn't matter, okay? So this is the linear momentum of body B expressed in frame S. How is it defined? It's defined as M multiplied by V. Okay? This is just a result of taking the gradient with respect to the V for the kinetic energy. Now, how is the dynamic equation? We have only one equation that we know of, okay, in mechanics, which is just Newton's law. How is Newton's law defined? F equal to? Completely wrong. That's not what Newton said. Okay? This is exactly. The rate of change of momentum is equal to the total applied force on it. This is Newton's law. There's still something missing. This is not also what Newton said. He put actually a condition there. Of course, in physics, you forget about it. Who can guess what it is? It has to be in an inertial frame. If you have numbers and you write them down, Newton said that you have to represent these numbers in an inertial frame, a frame that's not moving. Okay, so the rate of change of momentum in an inertial frame is equal to the sum of all of the forces that are applied. And forces, you can sum them, so you can just say I have the resultant force. Or simply, the momentum itself was equal to m multiplied by v. So it is equivalent to saying that v dot is equal to 1 over m multiplied by f, which is nothing else than acceleration is equal to f over m, or f equal to ma. Make sense? Okay. So now we see we introduced 3 equations, and this is nothing else than just a block diagram to describe this dynamics of a point mass. You have the forces, okay, which are equivalent to the rate of change of the momentum in the inertial frame, in the S frame. You integrate it with some initial condition. You multiply it by m inverse, you get the v. You multiply, the v is equal to psi dot, right, the rate of change of the position. And you integrate the position, you integrate the rate of change of the position, you get the position. Okay, yes. Just a 3 by 3 matrix, okay? Identity. Okay, just to put something in a block. Okay, because this is something, they're different things. This is force and this is rate of change of momentum. That's the only reason. So the rate of change of position is equal to velocity. This is known as a kinematic equation, the kinematic relation. The rate of change of momentum is equal to the total applied forces. There is nothing else than the balance of momentum. And the relation between V and the linear momentum is nothing else than called actually a constitutive equation. You see that these equations, they're independent of how big or small the body is. They're always valid, right? And you see here the M was actually the only thing that has the body itself, And this is the only thing that, we're talking about how big this body is, or how small is it, or how heavy is it, and so on and so forth. Okay, so this is usually the separation of these 3 variables. Of course, you're used to them just combining all of them together into one simple equation, which is A is equal to 1 over m multiplied by f. Okay, f equal to ma. But you're canceling out all of this, okay, equations. Now, what is the problem of thinking about this in this way? That you see here, position is R3, velocity is in R, so rate of change of position is in R3, velocity is in R3, momentum is in R3, rate of change of momentum is in R3, forces are in R3. Everything is R3, everything is nice. Now go to rotations, you're screwed. Okay, cannot do anything.
Free particle also is point mass, or what?
The free particle is a point mass, yes.
Could be said as a free particle.
It is a free particle, yeah, absolutely, yeah. It is a free particle. Any questions? How hard do you think it will be now to go to rigid bodies? Let's see. Okay. That's right. But if you have the correct tools, okay, let's see. So what we need to do is that we need to just draw an analogy between what we talked about for point masses and rigid bodies. We just need to give the correct structure. We just need to use the correct tools, the correct math, and let's see if everything actually will be, hopefully the same. We're going to be introducing what's known as the wrench. So a wrench, SRC, acting on B, just denotes the abstract wrench from source SRC acting on body attached to B. You can have many sources of wrenches. For example, if I have a drone and I have one propeller, this propeller is actually acting on the body with some wrench. If I have another propeller, this propeller is acting with another wrench, and so on. So for every propeller, I have one wrench acting on the body. Then I have also gravity. It's trying to take the thing down. If you're inside of a fluid, then whenever you move, you have hydrodynamic wrenches and so on and so forth. Okay? So you see, this is where the SRC comes from. You just have multiple sources. If I represent it in a frame, I just put this frame explicitly, okay, with this comma like this. So this is the star, which will be the numbers in which we're going to be representing it. Here now, I have either in the B frame or in the S frame or in any other frame. Okay? So always, this is very important. Okay? You're not bound to these 2 frames. You're bound to, you can represent this wrench in any other frame. Of course, depending on, on the problem. So this is what the wrench is. How is the kinetic energy defined? The kinetic energy defined is half the twist transpose multiplied by something like a mass, something like an inertia, multiplied by the twist. The twist, what was the size of the twist, this vector? 6x1 vector. So this is half, what, and the kinetic energy should be what? In fact, a scalar, right? So it doesn't, the kinetic energy does not depend on any frame. It's just a scalar. So this is a 1/6. This is 6x1. What should this inertia map be? 6x6 matrix. Okay. This 6x6 matrix, the question is it a map from R6 to R6 or from R6 to R6 star? Or doesn't matter? For now, this is actually a map that will take you from R6 to R6 star. What was the name of this map? Anyone remember? Bilinear map. A map that takes you from R6 to R6 star was a bilinear map. The covector is actually the wrench itself. The wrench is a covector, but the inertia is a bilinear map. Sorry? It's a okay. It's a covector of the space where the twists live. So the twists are vectors, and this is the covector that corresponds to it. Okay, and you're going to see exactly what that means. Excellent question. Come to that later. Okay, keep it for later. So this is what the inertia matrix. I'll tell you how it looks like, but just something so that you know. In general, it's not a constant. Okay, in general, it's a function of h. And it depends on which frame you're representing it in. So this is what the inertia is. Okay. Now, okay, we're going to look at it in details in a bit. But for now, forget about it. Just take a look at this structure. It's half V transpose I multiplied by V. How is the momentum defined? Take the gradient of this expression with respect to the twist. What do you get? Simply this inertia matrix, which is a 6x6 matrix multiplied by a 6x1 vector. What is the result? A 6x1 vector. What is the nature of this numbers? You see here, if I told you that the inertia will take a vector to a covector, and now this is the inertia eating a vector, what should it spit out? A covector. So in the end, the momentum is actually a covector. It's not a vector. So now we have two things. We have wrenches and momenta. They are covectors. And the twist is a vector. Why? We're going to look at it in a bit. Okay. How do you think the Newton's law should look like in this expression? How is Newton's law should look like? You have rotation and translation, something that's, doing rigid, crazy stuff. How should Newton's law look like? It depends. It's a function of h in general. It's a function of h and the twist. This is exactly what you have. The rate of change of this generalized momentum is equal to the total applied wrenches. That's it. This is Newton's law. There is a catch here. What is the catch? The S. You have to represent this equation in the S frame, no other frame. So if I try to represent this in the B frame, and I say that the rate of change of momentum in the B frame is equal to the total wrenches applied in the B frame, it's false. It's not correct. This is not Newton's law. You need to represent this only in the S frame. Okay.
And we cannot represent the momentum in the body frame in terms of the S frame.
You can do that, and that's exactly what we're going to be doing. Okay? You can, it's possible, but at least Newton's law, which is that states that the rate of change of momentum is equal to the total applied forces. Now we're just going to be tweaking it with the correct math that the rate of change of the generalized momentum is equal to the total applied generalized forces, which is what we call the generalized forces wrenches. We call the generalized momentum, okay, because it was related through the generalized inertia to the generalized velocity, and the generalized velocity is what we call the twist. So everything is just rotation and translation in one package. No, you no longer have rotation alone and translation alone. Everything is just one object. For forces, you have wrenches. For linear velocities, you have twists. For masses, you have generalized inertia. For linear momentum, you have generalized momentum. And you get exactly the same expression as Newton's law. Okay. If Newton discovered this, he would be very happy. Okay. He was not the one actually that discovered this. Okay.
The forces or ranges lives in the tangent space also, or not?
That's a good question. Where do they live? That's exactly what we're going to be checking right now. But you can already guess that. So just from the information that we said so far, that twists, they are vectors. Inertia will map you from a vector to a covector, which means that momentum should be a covector. The rate of change of a covector is also a covector. And that's why we have here rate of change of a covector is equal to a covector. So wrenches are actually covectors as well. But how do we actually tell? Is there an easier way we can guess that? Can we check? So now I'm telling you that this is a vector and this is a covector. Let's say that you face in some, at some point in your life, something that's very new, and you don't know actually whether this is a vector or a covector, what is the nature of this object you're working with. Is there a way we can check? Any guess? What should we do? If you remember from what we did in vector space theory? Change coordinate, that's it. Change coordinate and see how it changes. Let's take a look. Now, let's take a look at a deeper look at the generalized inertia. The generalized inertia in general, no matter in which frame you represent it, it should always be symmetric and positive definite. This is actually inherent to that. In fact, it comes from the kinetic energy. Kinetic energy can never be negative, right? Can always be 0 or more. So that's why it can always be symmetric and positive definite. And it can only be 0 if the velocity is 0. So it's a symmetric positive definite function. We're going to be working later on with positive definite functions later on when we go to Lyapunov theory. But for now, just this is a feature of the generalized inertia. So if I tell you what is the mass of this object, you tell me what? It's 2 kilograms or 1 pound and so on and so forth. It's just a constant. You never say that if I have the body looks like this or like this or like that, its masses changes, right? So it always, it's just a constant. The inertia is also constant, provided you represent it in a body fixed frame. And you take a look here at any body fixed frame. Any body fixed frame, which means that if I tell you this is the body I'm interested in, and I put the frame like this, and it's moving with the body, okay? How is the inertia of this body expressed in this frame? By a 6x6 matrix, a constant 6x6 matrix, okay? If I change the frame and I put it here, okay, with different orientation and different location, is it still constant? It's constant, but it's not the same exactly. It's not the same matrix, but it's just constant number. What? Constant that new frame, exactly. Now you might be confused because you say that I always thought that the inertia, okay, if I have a rotation and translation, that inertia is nothing else than just mass and what you call a rotational inertia matrix, right? The J, the 3x3 matrix. If you ever did with the rotations, you have a 3x3 matrix that you call the moment of inertia matrix, right? How do I get this big 6x6 matrix? What is something here that's extra that you see there? There is this psi Cm in B. What do you think Cm corresponds to? Center of mass, exactly. There is an assumption that you've always done, okay, whenever you're working with, I don't know which course you took, rigid body dynamics, but you always say that the body frame is always attached where? At the center of mass. But not only that, you also made another assumption. What was it? Does anyone remember? It has a fixed orientation. How does it look like? But what if the body is like a potato? You always have something called the principal axis of inertia. There are actually 3 directions. If you represent the inertia in this frame, you get a diagonal matrix. You got 3 numbers. So in the end, you've always thought about inertia as just 4 numbers. 3J, right? J around the X, J around the Y, J around the Z, and 1 mass. In general, that's not true. This is the general form of the inertia. You have 10 numbers. 1, which is the mass, 6 in this inertia, and you have 3 for the center of mass. Because in the end, if I choose, for example, that this is the frame I have, and the center of mass is here, okay? Because now I'm not placed at the center of mass, I get actually some extra terms. And you've actually been introduced to this many times before under the name of parallel access theorem, right? If I have an inertia here and I translate it in this direction, I just multiply it by ml squared, right? So you see I have some sort of m, which is this, and I have some sort of distance, and there's like some square depending on how you translate it. This is the distance you see that appears in both ways. This actually will correspond to the ml squared sort of thing, okay? Of course, after you work it out. Of course. Here, this is, I never told you how you calculate all of this stuff. Okay, there's actually a very formal way. The engineering way how we do it is just, you take your object and you draw it in, your favorite CAD program, and it will actually calculate for you the J. Try this out for yourself. Okay, maybe when you're doing the project, you'll find that the program, for example, SolidWorks, will ask you, which frame do you want to represent it in? It will always tell you that. It will tell you, for example, it will always calculate for you the principal frame, the principal axis, and it will tell you actually what the principal axis looks like, and so on and so forth. Okay? But if you have a frame of choice, for example, if you have a drone that you said, okay, this is the forward, this is the left, and this is the up direction, then the inertia matrix in this chosen frame might not be just 3 numbers and 1 mass. It might actually have all of these extra terms on top of it. Okay. So in general, the generalized inertia matrix is just 10 numbers placed like this. It's a 6 by 6 matrix that looks like this. Okay. Question?
We put it in the center of mass.
Yes?
This will be 0, right?
Very good question. Yeah. So if we put the inertia at the center of mass, what will happen is that the center of mass location expressed in the B frame becomes what? Becomes 0, becomes the origin, because you place the B frame at the center of mass. So the center of mass, what is the coordinates of the center of mass? Becomes 0, 0, and 0. So this actually drops out, this drops out, you're left with this 6 by 6, so you're left with this 3 by 3 matrix and this 3 numbers. And in this case, you see that we just have a decoupling between the rotation part and the translation, but in general not. More on that in the homework, okay? And in the very good question. Let's leave that for next time. Next lecture, hopefully we're gonna start with this point, okay? Provided that you do the assignment before next lecture, okay? Because if not, then you'll not understand what I'm gonna talk about, okay? So again, I'm gonna repeat this for those who came late. Please do the homework and the assignment before next lecture, if you can. Right? It will save you really a lot of, you're gonna really hopefully connect all of the dots very quickly, okay? Compared to if you delay to next week, okay? And also there's a quiz next week, so that I can make sure that you really do it. Now, how do we change coordinates for the inertia matrix? I'll just give it to you like this, okay? We don't have there is actually a formula of how we can do it, but the inertia from the B frame to the S frame, just multiply from S to B here and from S to B transpose on this side. You remember now when we said that a bilinear map changes coordinates by some matrix and the matrix transpose before it. So it was P transpose, and then there was the matrix beta, and this was the P. And you see now exactly now that actually the inertia is a bilinear map. Okay. Now let's go to the question of why are momentum, okay, covectors, and why are twists vectors? Now you've seen so far that twists actually change coordinates by the adjoint, right? Remember what we discussed earlier? If I have a 6 by 1 vector, which is the twist, and I change coordinates from the B to S, I shall just multiply by the adjoint, okay, from B to S. How can I show now how the momentum changes coordinates? This is the exercise we're going to be doing now. Kinetic energy is a scalar. You all agree? Which means that if I look at it from the S frame or the B frame, this is the B frame, in the S frame, or in any other frame, I should get the same number. Make sense? The kinetic energy in the B frame, okay, you remember what we said, that it's actually just half V transpose inertia multiplied by V. But we said that if I have in the body fixed frame, the inertia becomes just constant. So it's no longer depending on H. I just have the kinetic energy as a function of the twist. There's no longer this dependency on edge. This is something mathematically you should always, be familiar with. When I say that I have a function of x and y, which is equal to a function of x, what does that mean? That the function is not depending on y. In general, I'm saying it's a function of x and y, but I'm saying that in this case, the y doesn't matter. Okay, so this is usually what this means. This is how the kinetic energy looks in the B frame. Now momentum is given by this expression. You all agree? What happens when I take momentum? So in the end, actually, we can take this equation. So this is the V transpose, and this is the momentum. Okay? Yes.
You said that E will always be B and S. Here it is both B.
That's a good point. Okay, so let me go back to that. That's a good point. You see here, and this is exactly why we have two indices. The index that you see here written, okay, the B one that's shown here, you should read it like this. This is the generalized momentum of the body attached to frame B, expressed in frame star, which means it could be in frame B, in frame S, frame Y, frame Z, doesn't matter. I can represent it in any other frame.
But star means the same frame, right?
No, star means any frame. All of these stars that you see here means any frame I choose.
Earlier when we had star, it meant that it has both the bodies have to be in the same frame, right?
No, which part? Which slide exactly? Could you remind?
When we were talking about the properties of quest,
Yes?
over there we said that for same frame, star shows that they are in the same frame.
Okay, so let me get back to that slide. That's a very important point. So this one, we're talking about this one, right? Take a look here. This is I with respect to K. This is I with respect to M. This is M with respect to K. You agree? Where are these three twists? Where are these three vectors represented?
Same frame.
In the same frame star. What is this star? Is it A? Is it B? But they have to be the same. That's exactly what I mean. So it can be anything, but they have to be the same. So if you go back now, fast forward to our slide here, you see that the momentum here, I can represent it in any frame. But the momentum is something corresponding to a body. You cannot say I have momentum of empty space. There's momentum of a body, momentum of the phone. But then I can represent it in this frame, or this frame, or that frame. That's exactly what it means. Clear now? Okay. More questions? If there's anything that's confusing, you have to stop me immediately, okay?
Frame of the body, star is a frame of the frame that we are relative to that body.
We are interested in.
You want where the numbers make sense. So for example, so this BS, so VBS with the star, what does that mean?
Frame B
Of the frame B
relative to frame S.
relative to frame S, some third frame. Some third frame, exactly. But momentum, you see, there is no something with respect to something. Momentum is just something that has one frame. The same also, by the way, for a wrench. When you say I have a wrench acting on a body, that's it. A gravity wrench acting on the drone, that's it. You see, it's just, and then I can represent it in the drone frame or in the inertial frame and so on and so forth.
Can be like force or the drag force.
Yes.
Acting on a drone.
Acting on the drone. Expressed in any frame.
Here, B of the star, of frame star, and
Which one? On the momentum, yeah.
B is the body itself.
The B is the body. It's not the frame. So here you have momentum of a body. That's why we're talking about momentum of the body attached to the body fixed frame B. That's the notation. This is what the notation implies. Okay. Clear? Yes.
Like here, when momentum comes from velocity, right?
Momentum comes from the gradient of the kinetic energy with respect to the velocity, yes.
So when the velocity is changing, it's relative from one frame to another, right? It's relative.
So when you change the numbers, or when so
And there are two frames. It will be different for both, right?
which frames are you're talking about the twist here, right? You're talking about the B and the S or the star?
Okay,
The B and the S, yeah, they are fixed. What do you mean by fixed? I mean that if you're describing the motion, for example, of the airplane with respect to the ground, then the airplane is B and S is the ground. And then the airplane is moving and the ground is fixed. And then where do you represent this vector? In any frame. It could be someone that's sitting on the airplane and he's watching the ground move. It could be someone sitting on the ground watching the airplane fly, or someone that's riding an air balloon on the side that's watching the airplane move with respect to the ground.
different for each of these parts.
Yes, absolutely, yes. The momentum for each of them, he will always say that. What is the momentum of the airplane?
That is what star.
With respect to, no, this is what the B means. With respect to where I am, the observer, exactly. So the star is always the observer. The star is always the observer, yes. Okay?
This is what I wanted from you.
Okay, perfect. Thanks a lot for pointing that. Is this clear for now? Okay. So again, so this is where we were. We took the kinetic energy in the B frame, and we just said it's half V transpose I multiplied by V. Okay. And we said that I multiplied by V is actually nothing else than the momentum. So we just wrote that twice the kinetic energy is nothing else than the V transpose P or P transpose V. You all agree? You look at this and the first thing comes to your mind is what? Say it. Sorry?
Group structure.
No. What's the first thing that comes to your mind when you look at this? X transpose Y. X transpose Y. What's the first thing that comes to your mind? Inner product. The dot product, right? Okay. So is this a dot product? No. There is no such thing as a dot product. Go back to the slide when we talked about the alpha and the V. We said they look like a dot product, but in fact, they are two different things. One is a covector and one is a vector. How do we show now that this is a covector and a vector? Simply change coordinates. If we have now that kinetic energy is independent of the frame, and I can write it as P transpose V, and the V itself is the adjoint from S to B, and I can take this adjoint, put it inside of the transpose, like this expression. Okay. So this expression, that's a new vector. It's a new 6 numbers, a new 6 tuple. Transpose multiplied by V in the S frame. I can just simply call this the momentum in the S frame. You see here, you see this expression? This is the transpose of the momentum in the S frame multiplied by the twist in the S frame. And you see here it's exactly the same as momentum in the B frame transpose multiplied by the twist in the B frame. Now take just pen and paper and compare both together. You find that if I have the twist in the B frame and I want to go to the S frame, I just multiply by the adjoint from B to S. If I have the wrench in the B frame and I want to take it to a wrench in the S frame, I just multiply it by the adjoint of the inverse, the inverse transpose of the adjoint from B to S.
Joint of inverse transpose or inverse transpose of joint?
This is the inverse transpose of the adjoint of HB to S.
First we take the inverse and then the transpose?
Yeah. Does it matter? Doesn't matter. Okay. And also the inverse itself. You remember what we said about one of the properties? The inverse of the adjoint is actually just the adjoint of S to B. Okay. This is another way of looking at it. So actually, if you look at this expression, you always have this. This is actually a very important, block diagram. If you really memorize it, You'll never make mistakes. You never have both directions going, okay, at the same time. You always have someone is enforcing the twist and the other one is enforcing the wrench. That's why you always have, if the twist is transformed from B to S by the adjoint, the wrench will be transformed back from S to B. Okay, actually, wait a second. I think, yeah, okay. All of this I already, okay. I ruined the surprise because this actually, we're talking, I shift for some immediately from momenta to wrenches, but this is what should have been for the momentum, okay? So you see here, I have from twists, from the B to the S, and this is momenta from the S to the B. If you look, so here we use the kinetic energy, right? If you look at the wrenches themselves expressed in any frame are just torques and forces, exactly okay what Ammar said, right? We have the combination. And if you pair a wrench and a twist, you actually get power. So when we pair momentum and velocity, we get twice kinetic energy. If you pair wrench and twist, you get power. You've already seen that before because what is force multiplied by linear velocity? Mechanical power, right? And what is torque multiplied by angular velocity? Also mechanical power. So of course, this makes sense that twist multiplied by velocity, again with this transpose, actually is also mechanical power. It's rotational power plus translational power. Just like exactly well, this expression of the kinetic energy is rotational kinetic energy plus translational kinetic energy. Everything is rotation and translation in one object. Okay? What do you mean?
Something like this.
So again, could you say it again?
That here in the block diagram.
This one?
The block diagram.
This one? Yeah. So here, B. So this is expressed in frame B. So you transform it from B to S, you go to S. And here you have a wrench in S. You multiply it by B to S transpose. So the B to S transpose is the same as S to B minus transpose. You see here? Yeah. So this has to be the other side. S to B minus transpose. Yeah. So we have to bring this the other side. Okay. Yes.
Okay, I have a question.
Yeah.
Here you mentioned that this comes from one source and this comes from another source.
What do you mean?
The twist.
Yeah, from this side and that side. Yeah. It will not be clear again what I mean by now.
Example, the wrench change the dynamics, cause the acceleration and the acceleration
What I said will not make sense. Hopefully 2-3 weeks. Okay. But come back to that, this picture again. That's right. R6 star. So this is R6, 6 numbers. This is R6 star. You might say, but in the end, I write it as 6 numbers, right? I write them as 3 on the top and 3 on the bottom. So what's the difference? The nature. This is a covector, and this is a vector. Absolutely. No, that's not true. To real numbers. And that's exactly what you have here, you see? This is the covector. In this case, it ate a vector, give you a real number. So is it a map? So if you look at it as 6 numbers, you don't see it as a map. If you put it as a row vector, it becomes a map. And that's exactly what we said earlier. Okay, the whole idea that the vector, that a covector is seen as a map, or you can take it as 6 numbers, okay, and you can think of it as another vector. And that's exactly where, okay, by vector here, I mean an element of a vector space, which is also true because the dual space is another vector space. Okay, so the only way to really see covectors and vectors is to write this equation. Look at how do these change coordinates. Now the question is, in general, is the adjoint the same as the inverse transpose of the adjoint? Never, they are never the same. Okay. Now a good question of Ammar was, when we had forces and velocities, okay, how do we change coordinates? Okay? We change coordinates by, I have to go back here. You see this expression? If I have an angular velocity, okay, and I change coordinates from the B to the S, what do I need to multiply it by? A rotation matrix from B to S, right? If I have a force and I want to multiply it from the B frame to the S frame, what should I multiply it by? The inverse transpose of the adjoint. Make sense? The adjoint itself is a rotation matrix. What is the inverse transpose of a rotation matrix? What is the inverse transpose of a rotation matrix? Should be again the same matrix. And that's why you never see the difference. You have the same R. Same matrix, yeah. But isn't R transpose R equal to the identity? That's the definition of the inverse. So the inverse and the transpose are exactly the same. And that's why you never saw the difference before. So if you work, so the whole story is that if you constrain yourself to point dynamics, everything is in R3. If you work in rotational rigid body rotations, you still have angular velocity and torques and so on. But when you change coordinates, everything is with the rotation matrix, which is an orthonormal map. Okay, so the transpose is the inverse. That's why you never see a difference between vectors and covectors. In this case, we went to the space of twists, and now you see clearly that even though both are 6 numbers, we need to transform them differently. So you need to make sure what is a vector, what is a covector. And of course, now not every matrix will be a linear map. Some of them will be bilinear maps, some of them will be endomorphisms. We have to be careful also how they change coordinates. And this is one of the examples where we had the inertia map, the generalized inertia, which is actually a bilinear map, changes coordinates by this way. Okay, you can have another example, okay, in the assignment of a map. Actually, this map will be the small adjoint. So the small adjoint changes coordinates by add and add inverse. Okay, so it's actually an endomorphism, not a bilinear map. Okay, all of them are matrices. Everything is, numbers, but you have to be very careful what is the object we're talking about. Let's see how much time we have. This is just the wrap of what we have. Okay, so this is just the conclusion that we have a kinematic relation, which is H dot is equal to H multiplied by V tilde. P dot, okay, in the S frame is equal to the wrenches applied on the S frame. And then you have here that the twist in the B frame is equal to the inverse of this constant inertia, generalized inertia, to the momentum in the B frame. Now, the natural question is, this is very nice, but I have everything expressed in the S frame. Okay, so as Tarek proposed, can we write this equation in the B frame? Okay. Yes, of course. And this is actually more popular, okay, because we need to work with that. Okay. I'm just going to show you how they look like, and then next lecture, inshallah, we're going to be working them out. And of course, you're going to be working them actually more out in the assignment. Okay, so you have to write them by yourself. Okay? So that's why I'm saying, okay, if you do the assignment before next lecture, you're going to win a lot of, a lot of information that will help you really understand and wrap up this topic before we move on later on to the manipulators. Okay, so this is how the equation will look like if we represent the momentum in the B frame. Okay, and there's another way that we can write it, okay, by just some sort of equations, and this will actually be very important later on when we start to do control. Okay, we're just gonna be working out both equations, 2 forms. It's actually not what. So the whole idea is that we have 3 ways of writing the rigid body dynamics. Okay, but that's for later, inshallah. Okay, strongly suggest you do the assignment and the homework. Okay, before next lecture. Okay, so let's stop here. So see you inshallah on Tuesday.